Good afternoon, my name is Sylvester Jallo. Today I'll be talking about Quaternion. Today my discussion about Quaternion is going to cover the functional in real world, mathematical history, operation, and rotation. So let's begin. Quaternion is used for many aspects in life. Most of the time it's 3D representation in which the reflection, rotation, and scaling of the figure can be rotated, scaled, and do it using Quaternion formulas and Hamilton invention of Quaternion. The important of Quaternion is basically for abstract algebra. Hamilton invented it, helped a great deal into extend the understanding of abstract algebra. Quaternion method can be used with an automorphism for 3 to 4 dimensional space, mostly in computer graphics and navigation system. It's used in math such as control theory, signal processing, altitude control, physics, orbital mechanics, and numerous other math fields. So now we talk a little about Quaternion and what it's used for. Let's talk about the structure. The structure of Quaternion, as you notice, is kind of similar to complex number. And it's a complex number has imaginary and a real part. Quaternion is just the extension of that. It has one real part, and 3 imaginary. The 3 imaginary has I, J, and K, which will have a different axis of rotation in a clockwise rotation. The operation of Quaternion is just a complex number. All the operations are the same except for multiplication, which Hamilton got stuck on. We'll talk about that later on. Quaternion, each letter I, J, and K represent the square root of -1, just like I did in complex number. Quaternion system are basically associative, non-abelian meaning non-commutative. So if you take K times I, will yield you a different result than I times K because of the clockwise rotation going backwards. Each non-zero contains multiplication inverse, and it has also a conjugate. The letter used to represent Quaternions is Q sub 8 or H, which is basically named after Hamilton, the inventor of Quaternion. And it has an order of 8, meaning it has 8 elements. Plus or minus 1, plus or minus I, plus or minus J, plus or minus K. Let's talk about the structure, more about the structure. Okay? Like I was telling you before, Quaternion is non-abelian, meaning it's non-commutative. So you can take, for example, K times I is equal to J, right? So if you start the K axis and you rotate towards the I axis, you go J. But now if you go in the reverse order where you go I times K, you will get a negative J because it's a clockwise rotation. So you go in reverse order. So that's what Hamilton got stuck at when he was trying to do his multiplication. So it's possible to do multiplication and to show a division, but the thing about it was the rotation. You should multiply 2 letters, you get another one, but when you do the reverse order, you are unable to. Okay, that's the structure right now. Let's talk about the history about Quaternion. We're going to start with Benjamin Rodriguez, who was the first person to start with Quaternion. At the time, it was unknown. Benjamin was born in 1795 in Bordeaux, France. He was a French banker, a mathematician, as well as a reformer. So he did all kinds of trades. In 1815, he was awarded a doctorate in mathematics at the University of Paris. And when he did the day sortation, we call it now the Rodriguez formula, is used widely. In 1825, he published a work on social reform, banking, which causes other math work to be ignored. Because basically a mathematician, other math people consider him not to be a mathematician because his work is basically on banking and reforms and other stuff like that. However, in 1840, he published a work called Transforming Group, which led to the discovery of Quaternion. At the time, it was ignored, but later on, it was discovered prior to William Hamilton. So let's talk about the inventor of the Quaternion. The inventor of Quaternion was William Warren Hamilton, born August 4, 1805 in Dublin, Ireland, where he spent the rest of his life. His father was always on the go, so he was raised by his uncle, Reverend Hamilton. In 1822, he discovered an important error in Laplace's treatise and called the celestic mechanics. He caught the eye of the world astronomer. At the time, the world astronomer was the professor of astronomy at the College of Dublin. And in 1823, Hamilton attended Dublin. 4 years later, he was appointed professor of astronomy and astronomer of Rhode Island, so he took over the guy who discovered him, who said he was a prodigy. In 1827, he produced his first work, Theory on System of Rays, over the theory of optics. November 1830, he became obsessed after reading a paper of a complex number and algebraic couplets. He was so obsessed that his graduate work considered complex number using the order couplets of A and B, which he coined the word vector, which is now used throughout math to show the rotation describing the algebraic couplets. So he used the two letters, the A and the B of the imaginary parts, to describe the couplets and complete the multiplication, addition, and so forth. He was hoping, he was hoping to develop a three-dimensional analogy of complex number. However, he was unsuccessful because he couldn't multiply. He was in an attempt to allow the division, he wasn't able to. So he spent several years trying to figure that out. But however, on October 16, 1843, while walking on the Royal Canal in Dublin, he realized that it required two imaginary parts. It required three imaginary parts, and it required one real number and two imaginary parts. I made a mistake right there. His discovery continued on October 16, 1843. He spent the next 20 years trying to apply continuum to problems in applied math. Spent a whole time trying to deal with this. However, his study led to the discovery of Hamilton mechanics, which was vital to the field of mechanics and electromagnetic. However, in 1865, he's still living in Dublin, where he spent most of his life. William Warren Hamilton died. I left a stem to enrich the island and commemorate his triumph discovering Quaternion. Okay, let's look after his death. When Hamilton died, he had several predecessors that continued advocating his use of his work. In 1865, two people, Peter Trace and Benjamin Pierce, said that continuum can be used in physics and geometry to describe vectors. Hamilton coined entering through continuum, entirely through continuum. However, in 1880, continuum began to be displayed as a vector analysis, in which he developed Joshua Willard and Oliver Hirschfeld. So these two people also continue advocating that continuum can be used to describe vectors, analysis, and numerous other stuff. Now let's talk about the rotation and continuum basically used in math. Well, continuum is used in 3-dimension and 4-dimension, but rotate stuff because it's very, very important. Each universe is considered axis, so X, Y, K, J, and I are considered axis of rotation, representing the imaginary parts. Q is computer rotation by the unit vector by the angle. So if you want to rotate any images, you take it times Q by this angle. Okay. So the vector, for example, this vector X, I, Y, J, and Z, K, which I, J, and K represents the axis of rotation. The vector can be rotated by angle through the linear operation, as I give you right there, with Q times the vector times the conjugate, which Q is rotated by the angle, cosine the angle divided by 2, times the vector sine theta divided by 2. Well, when you rotate it by the angle and taking the conjugate of it, it leaves the vector length the same, the direction is not effective. So you can still rotate it, but it leaves everything the same. I'll give you more in depth about the formulas. It's how the rotation was calculated. At the bottom, which is Q, V times the conjugate can be written as, where Q is SV, and the conjugate of SV is basically just a minus sign to the complex part. Okay. In the vector, so you just switch the sign of the vector. If you do the operation, you can find out that it's not altered at all for the rotation to occur. Since all continua are hypersphere multiplied by another, it will yield a third continuum, meaning that it will get you back, will stay in the same group. The continuum operation is interpreted as a point of vector rotation with respect to the fixed coordinate plane. Continuum represents two things in rotation: the axis which is being rotated and the angle which is being rotated by or through. Any continuum can form a vector of coordinate its rotation about the axis of Q through the angle. Like I said before, any continuum can be rotated to the angle. Pauling spin matrices. The important spin matrices in relation to rotation is that Pauling spin represent observable spin in three spherical direction. The Pauling spin matrix is just a 2x2 matrix in which any continuum can be written in. So basically, any continuum can be written into this form. We can basically complete the rotation using the operation. Pauling spin matrix is closely related because they're basically isomorphic to the continuum group. If you can see on the next slide, you can see that the Pauling spin matrix we represent, so I gave you 3 of them, is basically isomorphic to the continuum. In the equation, I gave you the continuum formula up there, which is H, but if you notice the U is the identity matrix, meaning it's the real part, and the other part is just complex numbers. Okay. Continuum can be expressed in the Pauling matrix, in which is written into a linear combination. So that's how you relate it. You can write into a linear combination. That concludes my discussion about the history of continuum, the rotation, and the using in relation to in life. I have a full question for you. What is the letter used to identify a continuum group? What are the 3 letters that Hamilton used? What do the square root of each represent? What is the continuum used for? How is Pauling matrix related to continuum group? And this concludes my topic about continuum. Thank you for your time. I appreciate you listening.